Okay, so this guy, he wishes to load a refrigerator onto this truck using a ramp. So this is a ramp with an angle theta. So he says that, the work would be less if only this length would be increased. Length would be increased. Hence, the angle would be lesser, where we now had to do some calculation and shows that the answer is would be the other way around. Okay, now there is an additional info to this question. Okay, the additional info that this question should say is it's supposed to mention that the refrigerator is to be wheeled at constant speed. So, for that reason, change of kinetic energy would be 0, a bit lost. Okay, remember that change of kinetic energy is half mass V final minus V initial. Since they are of the same value, both are the same. So that's the reason why where you arrive with 0 change in KE. Now let's wrap this off. The normal force by the ramp is directed 90 degree to the displacement, so it does no work. Okay, so in short, they are looking at the situation whereby force by the gravity. Okay, let's just draw something. We are aware that there will be weight here, there will be normal force here, perpendicular. So normal force will not contribute to doing work because it's perpendicular. So weight of the refrigerator itself, okay, would be equivalent to the weight or will be equivalent to the force applied by the man. That's what it tried to say. Okay. And work by the refrigerator is equivalent to something you have seen earlier, mg sin theta. Mg sin theta. So this is work by the gravity. So this is the work by the gravity. On the other hand, the man, okay, this man is as well applying force parallel and in the same direction as the motion. So this is delta R. Okay, so when we do a little bit of calculation, we will arrive with the idea, number one, they are opposite in direction, yet they are equivalent because change of KE is 0. A bit lost. Alright, hold on. Okay, let's go back with what's given by the book itself. Okay, if I were to start from this picture and also then map with the given equation, you will find that the situation is force by the man times the delta R. Okay, so this would be by the man, okay, by the man, plus mg sin theta, times the delta R and times cos 180. Okay, you might be tempted to ask why all of a sudden it's 180 here. Remember that the force of weight are directed to the right, positive direction, while the displacement is on the other opposite side. So that makes them in opposite direction. So 180 degree between them. So that's the reason why when you are calculating weight work by the man, it will turns out to be something like this. Okay, okay, it's plus, and then work by the man is now equivalent to work by the gravity. Okay, work by the gravity, and this is cos 180, so it turns out to be negative here, and then mg sin theta times delta R times cos 180 is negative 1. Okay, So the negative and negative will turns out to be positive. Observe here. It's becoming positive. And delta R here is now being replaced with L. So mg sine theta times L. Mg sine theta times L. Now take out the L sine theta. The L sine theta is equivalent to H. Okay, a bit lost. Go back to this figure. So this is how it looks like. This is the angle theta, this is the H, this is the hypotenuse. So as you relate with one another, you will find that L sine theta is equivalent to H. So you find that mg L sine theta through the ram distance is equivalent as if the work that he transferred the object, he transferred the refrigerator right from the very end here, okay, at the vertical height. And that makes it easy to say to him that, yeah, he is definitely wrong, that it doesn't depend on the angle. It depends only on the vertical height. So that's why it says that regardless of the length of the ram, the same amount of work would be applied. Okay. However, although last force is required with longer ram, the point of application of that force move through a greater displacement. Maknanya, even though force dia akan jadi kecil sikit, okay, the number one, the amount of work is the same. However, less force required with a longer ram. Cumanya, distance travel, R dia would be larger. So, to him, dia rasa macam, oh, it's easy. But the fact is, he had to travel slightly longer. Alright, for this portion, okay, we are going to look that work can be calculated as well by using version coming from potential energy. I'm going to start with another textbook first, and then we're going to go back to our textbook to find the correlation. Now, gravitational potential energy, for instance, okay, you have seen this earlier, that if you are asked to calculate potential energy, it should be mg times h or mg times y, the vertical height. Okay, for a reason, for instance, this is a case whereby a book that falls down by the gravity, falls down free fall. Okay, so you find that the force is directed downward and the travelling distance, or by using our books, is R. Okay, they are of the same direction. So we find that we might be tempted to write it as mg times delta R, okay, or y, okay, whatever symbols that you, as long as you understand that there should be a distance travel. And turns out the angle between them is 0. So cos 0. So if, for instance, we give values here, so this is 5 meter distance, this is 3 meter distance, and this is 0. So mathematically, it will turns out to be mg 3 minus 5. Okay, have a look. So it should be here only 2 lah, because cos 0. Okay, what I'm tempted to say is, you should arrive with a positive value. A positive value because it's travelling in the same direction with the displacement. Okay, now, when we develop an expression calculating weight, calculating work by the gravity, observe now, if we consider concept of delta y, okay, it will turns out to be something like this. mg times delta y, final minus initial. Okay, let's start. Okay, negative mg y final is 3 meter, initial is 5 meter. What do you see? You see that they ended with a positive answer, a positive times 2. Okay, so here, what I'm about to say to you, there is a modification of equation. Though we did understand the concept that they must be in the same direction or parallel or anti-parallel. However, we did has to consider that we can't straight away use this delta R by saying that 3 minus 5 as such, okay? Because or else you get stuck with just put it with a negative product. So this is wrong. So when we did the calculation of work, okay, so rather than trying to go with the whole distance travel and you would like to incorporate the idea of delta, then ensure that it becomes negative times delta y. Then only by expression it will compensate with the idea that in this scenario, yes, we arrive with a positive answer, same as this method. Alright, so in conclusion, if you are looking to calculate by using equation for work done by the force of the gravity, then it must be following this method. Negative force by the gravity and times a delta vertical distance or vertical, bear in mind is a vertical product. So with a vertical product, straight away you are already incorporating concept of cost, right. Now let's turn to our book. Now, turn to page 165, potential energy of a system. Now, in this example given by our book, it's very similar to what we've seen just now in other textbook, except that they are portraying the applied force. Okay, this is a situation where the book is traveling upwards. So, since it's traveling upwards, it needs to overcome the gravity. It needs to overcome. Minimum work required is just enough to overcome the gravity. So kita akan nampak dalam example yang diberi ni, the speed remain zero, remain zero because dia situation dia just enough je to overcome work by the gravity. Okay. So in that sense, we will find that force applied here is equivalent in value. Equivalent in value. Force applied and weight is equivalent in value. So we might be tempted to put that delta R would be Y final minus Y initial. Alright. However, why did I start with different textbook just now? Because the discussion here appeared to be using work external. So recall just now in the figure, if V is constant, then you will find that force applied has the same value as weight, and it's in the opposite direction, So you find that calculation of work by this force is equivalent to Y final minus Y initial. And the one that I like you to understand more is that if you were asked to calculate work by the gravity based on this expression, then you should see that the whole expression of this one would be times with negative 1. So negative weight by the gravity, work external. Okay, negative work external, and therefore equivalent to negative mg y final minus y initial. Alright, so because this is force applied, but here is work by the gravity. Okay, work by the gravity. So there's no such thing as they conflict with one another. They are just starting to discuss with different things sahaja sebenarnya. Tapi in all short, sebenarnya gravity calculation dia adalah negative work external ni sebenarnya, So which is negative mg change in y direction. Okay, so pegang yang ini. Tak pegang ni pun tak apa. Alright, now, so how are we going to use it? Work external. Alright, hold on to this. Okay. Alright, let's look at this example. Alright, let's look at example 7.8, which is supposed to be the last example coming from the textbook, but not from the examples. There is one more example to be covered in the additional example. So this is the case where all numbers given in this question is an approximation, approximation. So don't worry, during exam nanti kita akan bagi yang proper lah with numbers. So this is a case whereby a trophy being shown off by a careless athlete then slip jatuh and then drop onto his foot. Okay, now choosing floor ni as the y equivalent to 0, you kena estimate, anggarkan change in the gravitational potential energy. Okay, as the trophy falls down, change of the potential energy ni. Okay, so accordingly we will find that change represent final minus initial. Final minus initial. So the situation final is 0. This is the y final. So it's as if this is him, foot. Okay, this is 0. So okay, the 2 is slightly higher. Okay, so this is make it 0.05. Okay, now provided that the mass is not given, so let's just assume for this question, there are a statement here approximately 2 kilogram. So this is the 2 kilogram. The G value, remember that the G value is a positive value. We are not going to consider the negative, only in free fall and projectile sahaja. And then the distance when he hold it on top, okay, it's 1.4 meter. Okay, it's from the upper part of 1.4 meter. So he was perhaps holding it at this level. Okay, most probable. So let's just use red color to indicate the direction. So this is where it started and this is where it landed on his foot. So y final, So you will find that changes is by this number 0.98 minus 27.4 joule. So you just plug in the number of the idea final minus initial. Okay. However, if let's say that the question is asking what is the work done by the gravity, okay, on the trophy, then observe that the answer should be negative change of the gravity, or in different textbook they use different symbols, change PE. Okay, so you will find that the answer is now negative 26.4 joule. So positive 26.4 joule. So since it's a positive number, you will find that the trophy will experience larger velocity by the time hitting his foot. Alright, by the time hitting his foot. So by right, if you write down as 26.4 joule, you can now write it again in a form of change in kinetic energy, calculating the V final and V initial. If let's say that start from 0, then you might you can now calculate what will be the V final by the time hits the foot, okay, the top of the foot. Again, this is an additional concept, okay, of gravitational potential energy. Yes, it has the same unit as work, which is joule, same unit as kinetic energy, which is joule as well. Right. So this is the one that I have mentioned earlier. So if it's a change of that, you will find the expression. Okay, the expression work is equivalent to negative change of potential, or given by your book just now, negative change in the gravitational potential energy. Alright, hold on to this. We are not going yet looking at this, but at the end of the day, when we goes into a next topic, you will be widely exposed to this type of equation. Okay, let us go back to our textbook. Okay, we're going to look at the idea of elastic potential energy, which we have seen earlier that work external overcoming the force by the spring, okay, is equivalent to the change of elastic potential energy. So this is the expression, yeah, change. But if you are talking about work by the spring, then just opposite of this equation, okay. So it becomes half kx initial minus half kx final. Dia terbalik sahaja because of the concept that it's opposite to one another. Force applied and force of the spring are opposite in direction. But nevertheless, I'm interested actually to discuss on how energy changes with one another, but they remain the same. Alright, we have 3 columns here. Number 1, kinetic energy. Represent speed, yeah? Represent or correlation with the speed. Or perhaps you can say velocity, okay? Potential energy because of the displacement, the x or the r, and then the amount of total energy. Now, by not touching or do anything to the spring, you find that the energy of the system is considered as zero, So you find that when you do compression or after that there was movement, so you find that there will be energy, okay, involved here. And the amount is equivalent. So look at the total energy, 100, 100, 100. Okay, sorry, here is not 100 yet. Okay, so this is 100, number C, uh, BCD, I think. Okay, so they were trying to correlate that while object is being compressed, they compress, the amount of energy remain the same. It's just that they changes the amount. So let's start with the last one. You find that the kinetic energy 100, potential turns to be 0. D, the kinetic energy somewhere larger than 50, but this one is the balance. But if you add up, they turn up to be 100. Understand? Okay, now, while this one, all the energy is in the form of potential energy. So the total amount is adding kinetic plus potential. Alright, here is actually when it's partially compressed. It's halfway being compressed, okay? Halfway being compressed. So that's why potential energy really just proportional to the amount of the compression sebenarnya. Untuk B ni adalah dia baru nak tolak, dia baru partially. And then this C, however, dia dah compress maximum. And bila D, dia lepaskan. Bila lepaskan, you find release, release. Ni compress maximum. Maknanya kita kena bayangkan tangan kita dekat sini ni. Our hand push it and then we release it. The moment we release it, the energy yang kita supply by pushing force applied tadi, dia akan tukar bentuk because potential tadi yang kita bekalkan tadi now converted into motion kinetic energy, makin laju. And we find dia paling laju sebenarnya masa dekat x0 lah. Okay, pada 0 dan dia dah lost contact with the spring. Okay, lost contact to the spring. Alright, another things to note as well, kalau kita bermain sikit with the expression, we find as well that half potential energy ni can be calculated again based on half kx squared. So kalau x dah jadi kosong, x turns to be 0, then it means that the all the energy now is in the form of ke. Okay, dah full dekat ke. Okay, I was about to meningkatkan but it's not correct. Okay, so all are being converted into kinetic energy, or by the book symbol used adalah k, but never mind. Okay, they are just symbol. Alright, we've seen this before, the concept of work external force, on elastic potential energy. I don't wish to go detail into here because at the end of the day you find that there are many approaches to the idea of work. So in short, we need to do mind mapping to see the whole picture once again, right? Now let's look at the last subtopic. This subtopic, conservative and non-conservative, would be the core idea and would be used frequently in the next topic, which is chapter 8. Now, here, term used is conservative and non-conservative. Okay, let me just be frank with you. When it start talking about non-conservative forces, it's actually referring to friction. The force that is non-conservative is friction. When it start talking about conservative, it's actually weak or the gravity force. Okay, gravity force. Now, we will look at the idea so that you understand why is it so important to differentiate between these two. Okay, to differentiate between these two. Alright, the book tend to discuss it ataupun the approach is using the concept of internal energy. When it start saying internal here, it's actually referring to the gravity. It's actually referring to the force of the gravity. Okay, mg lah. And what else? mgh. Internal energy. So mgh, mgy. Nevertheless, it's energy coming from the gravity. It's all about that. Alright, we are not... Okay, this is it. Alright, I am not happy with given example here. Let's go back to one example you have seen earlier. Turn to page 164. The conceptual 7.7. Remember this example whereby you ended with a conclusion that regardless how it moves, whether through the ramp, okay, let me show you the ramp itself. Okay, so if you move through this distance or this distance, you find that you arrive with the same answer regardless. In fact, you can have a longer ramp but the same height. You still arrive with the same amount of work. This is the idea that work by the gravity. Gravity is a gravity force is a conservative force. Okay, conservative force. So in short, conservative force, it does not depend. It doesn't depends on the path it takes. It doesn't depend on the path. For instance, just now, longer distance ke, the shortest distance possible ke, at the end of the day, it does not depend. Dia cuma depend on the vertical height sahaja. Okay, and that is the reason why gravity force ni is considered as a conservative force. Now, let's look at this quick quiz. This is coming from different textbook. Again, it's survey. Whereby the situation is this guy is going to throw 3 identical ball, sama mass, from the same position, from the same height, from the same gravitational potential energy, right? And same initial speed, same kinetic energy lah. But only the difference is at different angle, macam projectile, right? But you will find that from the topics of conservation of energy, okay, when this happen, when these 3 identical, same initial speed, same height, one is thrown horizontally, second at angle above horizontal, and then one is below. When they ask you to rank the speed from fastest to the slowest, you will find that the answer is all will strike with the same speed. Why? Because initially they have the same energy, the same total energy. Okay, so when you go back by using the concept of work after this, okay, you can actually arrive and show that they will end with the same speed. So that is again the idea, the generic idea that gravity is a conservative force. Alright, now let's get back to our book 170, right? So in overall, we can say that conservative force has these following properties. Okay, this is the most common. Okay, that it's independent of the path taken. That's the keyword. Dia tak kisah ikutlah jalan mana, longer, shorter, but it's independent. So number 2 is less lah. Okay, you will find that different book dia tak define yang ni. So it says that the path taken is a closed path. That work done through the closed path, the net work, okay, the work done is equivalent to 0. So when you add all the amount of works, okay, on the particle, so you find that the total work is equivalent to 0. That's number 2, right? Therefore, from the character just now, from the property just now, when we try to satisfy what is non-conserve then, okay, apa yang tak conserve ni? Okay, so it's just the opposite, that it is path dependent. Jadi bila when we talk about friction, for example, when we talk about friction is what? Opposing force that oppose the motion. And then in the case of friction between surface, you find that larger distance, ni nampak ni, the red one ni larger distance kan, but you still end with the same position kan. You start with A and then you end at B, but you take different distance. So you find that the red one is actually greater, work dia greater. Sebab bukan work tau, work friction is greater, bukan work done. Work by the friction is greater because it has a longer path taken. Alright, let's look at this example. Now, in this example, you will find that you are going to do the integration. Why? Because in this, you have no constant force, and in fact, you are given an equation to describe the force. Okay, an equation, and that's the reason why we are going to turn into using this technique. Kenapa? Sebab kita diberi equation. Jadi kita guna konsep equation lah. Macam tu. So this force is a conservative force, and then mass is 5.3, and then the force equation is such. Then as particle move between 0.96 and 4.7 ni, maknanya ini initial, ini final. Calculate work done by this force. Siapa buat kerja? Force ni. Jadi kita kena tengok lah work by this force. So work by this force, concept of integration, we are going to do towards the x. Therefore, if you remember, the technique is the index just now. Okay, the index. This is the index just now. Add with 1. Okay, and the new index will be divided. Okay, so you arrive at this one. This one, the index is 0. So add 1, then divide by the new index. So 1. So become 4x. Okay, and then substitute the limit. And you will arrive with this answer. Okay, faham ya? Alright, how about the change in the potential energy? Now, change in the potential energy and work done, if this is a conservative force, straight away they have the same value but in opposite sign. Nampak ni? 36, negatif 36. 36.1, negatif 36.1. Alright, no argument for this case. So, negative change of potential, or perhaps similar to your textbook, the expression is negative change in U. Alright, so how about C? Kinetic energy of the particle at x if the speed is 3 at 0.9 seconds. Okay, let's just rephrase this. This is kinetic energy. The question is actually asking for kinetic energy final. If kinetic energy initial is given as from, so this kinetic energy initial is given as 3. So this is mass and then 3. Okay, so what to do? Use work energy theorem. Work energy theorem give you work equivalent to the change of kinetic energy. Okay, nak kenapa tak masukkan negative 36.1? Because this is change in potential energy. So what we did is we substitute sebenarnya work by the force in this scenario. Force apa ni? Force by the expression yang ini. So force by the expression here is the one you have calculated A just now, 36.1. That's why you substitute 36.1. Jadi, it should be something like this. The final, the final is unknown. Okay, look at it. Okay, this is unknown and this is one. Okay, that's this one. M times initial speed just now. Okay, and then just minus with one another, you will arrive with 60 joule. But the key element to understand of the work here, which work? You might get confused. Okay, so the work that you have calculated based on the force you are talking about. Okay, so this one, the force dia adalah yang ini. So what is the work by this one? Alright, in 7.8, relationship between conservative and potential energy, we actually have done this before. Okay, how you have seen this idea before, where rather than we write as internal, we write it as in a form of gravity. Why? Because gravity is a conservative force, alright, and we tend to write it as this negative change in internal, negative change in the potential energy. That's the core idea. Okay, that's the core idea, the expression to be used. Alright, let's wrap up what is 7.8. Alright. Now, energy diagram. Alright, energy diagram and equilibrium of a system. So, what is equilibrium? This, number one, what we are talking about is by referring to motion of a mass at the end of a spring. So, stable equilibrium represent the center. So, object, when it's acted by a spring, okay, or potential energy in a spring, you find that it's always trying to go to the equilibrium, nak balik pada keadaan asal dia. Okay, so you can see given here how the energy of a graph, okay, energy diagram, how kind of potential energy changes. Actually yang ni tak ada gonna rub off. Macam mana dia terlebih ni? Okay, the potential energy just stop here actually. So you find that this maximum energy is the total amount of the energy. So what we are going to do is we are going to incorporate kinetic energy into this diagram as well. And for that, I'm going to use different color. Hence, this is something we are going to put it as energy. So you find that the kinetic energy, okay, when it's at zero, all the energy belonging to the potential will be converted into kinetic energy. Okay, so this is one single coordinate. And then when it is at the maximum amplitude, we call maximum compression here, all energy is in the form of potential energy. So during that time, it's almost like trying to U-turn, nak U-turn balik. So momentarily it will stop. So that's why the kinetic energy would be zero here. And that goes the same as this one. So as we combine, we find that the shape of the energy belonging to kinetic energy and potential energy would look something like this. So the red curve just now belonging to the kinetic energy. The maroon one belong to the potential energy. Alright, let's compare with something from the online. Okay, so this is the maximum compression. This is the energy total. We find that at this location, compression, the energy are total in the form of potential energy. While when it is at zero, no compression, or the energy is in the form of kinetic energy. So this is how the energy diagram of a spring looks like as they move back and forth between negative x and x max. Okay, in different textbook they tend to write it as a, negative a. This is A. So to indicate the concept of amplitude, where amplitude ni sebenarnya sama je konsep with A maximum displacement. Alright, that's all and the core concept of chapter 7, the core concept. The rest are probably makeup and such lah. Okay, so we will find tunes this topic in the next topic, which is chapter 8. Stay tuned for chapter 8. Thank you.